Well, hey there, kiddos. It has been a while, but here we are. We're going to do a video over graphs of exponential functions. You got introduced to exponential functions yesterday, what they look like, how quickly something can get really big or really small. Today we're going to talk about what those graphs look like. And so the first thing it asks us to do is to complete this table of values for this function. It gives you a process column where you can show the work that you did, but y'all all know by now that we can take our calculator and we can type that into our calculator and just fill in the table from there. So I'm going to skip this process column and I'm going to go to my calculator and I'm going to type into y equals, I'm going to put 3 to the power of x. So if you're not sure what that looks like, here's what you do. You go to your y equals, clear out anything that's there because we don't need anything but the one equation we're going to type in, and it's 3 to the power of x. So you hit your 3, and then this caret top button right here, this little housetop looking thing, is your to the power up button. So I'm going to do 3, and you see it made a little exponent here, to the power of x. And so that's our function, and I need to fill in the table. So I'm going to go second graph so that I can look at the table, and then over here on my table I'm going to fill it in. And so the first one is at -3. And so when x is -3, you'll see if you're looking at your table that when you have to the -3 power and x is -3, you've got this really weird decimal. Well, let's go back and review what we know about exponents. And so really what we have, and I said I was going to skip this process column, I still am, but I need a place to write. So I'm going to erase my squiggle. And so what I really have is 3 to the -3 power. And if you remember way back when we learned about exponents, this is not acceptable. We have to write this as a fraction, and so this becomes 1 over 3 to the 3rd power. And so if I do that math, 3 to the 3rd power is 27. So if x is -3, then f of x is 1 over 27, which if you divide that in your calculator, you do 1 divided by 27, I'm willing to bet you get that really weird decimal that we were just looking at in the table. And so as an ordered pair, it's -3 and 1/27. And so then we have 3 to the -2 power, which works the same way. If I'm going to do that, remember that's 1 over 3 squared. Well, 3 squared is 9, so that's 1/9. So my ordered pair is -2 and 1/9. And I'm getting all these fractions. We're going to talk about why in a minute. The 3 to the -1 power, remember, is 1 over 3 to the 1st, which is just 1/3. And when you look at your table, that should say 0.3 repeating. And so you have -1 and 1/3. So you see I go from this really small fraction to a bigger fraction to an even bigger fraction. And then when I do 3 to the 0 power, remember way back when, exponents, we learned anything to the power of 0 equals 1. So that ordered pair should be 0, 1. And then when I do 3 to the 1st power, that's going to be 3. Because anything to the 1st power is just itself. And then I have 3 to the 2nd power, which is 9. And so here are my points. And so this is the table of values, and this is what happens. So what I have is an exponential function, 3 to the power of x. And so what happened is it started out really small, and then it got big. It didn't get really big. 9's not a huge number, but from 1/27 to 9, that's a pretty big jump, and it happened pretty quickly. And so that's what we want to talk about and what we want to see. So now we're going to graph the function, and we're going to use those points. We're going to plot those points to do it. And so I'm going to start with this one, the 0, 1. It's right here, so that's the y-intercept. And then I have 1, 3, and then 2, 9. And then the rest of them, it's going to be an estimate. I have -1 and 1/3. And then I have -2 and 1/9, which is smaller than 1/3. Then I have -3 and 1/27, which is smaller than that, and it just keeps getting smaller and smaller and smaller. So did my dots. That's funny. So when I connect those, this is what my graph starts to look like. And so from right to left, that graph is increasing. It's getting bigger, and it's getting bigger really quickly. We're going to talk about what happens down here to the left later, but that's what the graph is going to look like. And so it's a curve, like the quadratics we've been talking about, but it doesn't make a U. It's not symmetrical like the parabolas we did with quadratics. It's just a curve, and it's a sharp curve. It gets really, really big or really, really small depending on the data that you have really quickly. So definition of an exponential function. It's a function that can be written in this form. Y equals a times b to the x, where b is the base. We're going to talk about what that means more tomorrow. And a is the scale factor. And we'll talk all about that when we start talking about equations of exponentials. But for today, all we want to do is talk about their graphs and what happens and what do the numbers mean and all of that. And so, for f of x equals 3 to the x, the function we just graphed, is it increasing or decreasing? Well, that picture that we looked at from left to right, that's increasing. It was getting bigger. Those numbers got bigger. So it's an increasing function. The y-intercept, well, it crossed the y-axis at 1, so it's at 0, 1. Now we're supposed to find the value of x where y equals 0. Well, if you go to the table on your calculator and you look at your calculator and you look at these numbers in your table, and we keep going, they keep getting smaller, and so we're going to keep going, backing up and backing up. Now these are all in scientific notation because the decimals are now too long to fit in that little space, and so they're just writing them in scientific notation, but we keep going and we keep going, and I can do this all day long. And these numbers are going to get smaller and smaller and smaller and smaller, but they're never going to reach 0. It's like when you did the paper folding activity. You could keep folding that paper, and you're never, ever, ever going to have no paper left. You still have a sheet of paper. You're never going to have a fraction of that paper that equals 0, no matter how many folds you make. And so it's not going to equal 0. So the value of x where y equals 0, we just say that it does not exist, because there is no value of x where y equals 0, as it's not going to ever equal 0. It'll get really, really close, but it's not going to equal 0. So now it says find the average rate of change between 0 and 1. Well, that's what our table is for. Average rate of change, that just means slope. So what I need is my change from here to here. Well, from 1 to 3, that's an increase of 2. And from here to here, 0 to 1, that's an increase of 1, which means my average rate of change there is y over x, so it's 2 over 1, which is just 2. The average rate of change between 1 and 2, I'm going to do the same thing. My change from here to here, well, that's a plus 6. This is a plus 1. And so now my average rate of change is 6 over 1, or just 6. So now my rate of change is even bigger. And I could keep doing that all the way through, but that's what sort of why this, I mean, it's exponential. And that's what's happening. It's increasing, and it's increasing very fast. Now the domain of the function, it's got arrows on either end. It's going to the left and to the right forever. So we get to say that it is all real numbers. For the range of the function, we just have to say that it is everything greater than 0. You cannot say greater than or equal to 0, because like we talked about a minute ago, it's never going to actually equal 0. It's just going to get really close. So now we're going to make some predictions. Before we touch our calculators, I want you to think, what would happen if I took that 3 to the x power and I multiplied it by 2? So I did 2 times 3 to the x. What's going to happen to it? Is it going to increase faster? Is it going to decrease? Is it going to increase slower? What's going to happen? So make a prediction, and then we're going to go to our calculator and graph it and look. So if I go over here, now I want to do 2 times 3 to the power of x. And over here, I'm going to leave the original one. I'm going to leave 3 to the power of x in there so that I can see what would happen. So here's the new one. And then here is the original one. I'm going to draw it in red in just a second. There it is. And so now that one's in red. So the red one's the original, the blue one is the new one. And so what did happen? It increases faster. And what happened, if you look, I don't know that it increases faster, but it moved it up. You will see that my y-intercept is now at 2 instead of at 1. So I multiplied it by 2. I have now increased my So now what we're going to say is that if I multiplied it by 2, then it's going to increase faster because my numbers are going to get bigger faster. So now what would happen if I did multiplied it by a negative? So instead of 3 to the x, I did negative 3 to the x. Think about what happened when I did lines with a negative, or even parabolas or quadratics with a negative. What happened to those graphs? So let's make that prediction, and then we'll go look at them. So we'll go to our calculator here, and we'll do the same thing. This time we'll do negative 3 to the power of x, and we will graph them both and look at them. So there's the negative one, and then the red one will show up in just a second, and you will see it's positive. So there's the original, and here's the new. And so what happened is I took this red one and I reflected it. I flipped it over the y-axis. And so what happened here is it is reflected. So when I made it negative, now it reflects. So let's look at a couple more. So we're going to complete this table based on these two graphs, 4 to the x and 1/2 times 4 to the x. And then we're going to compare them, talk about them, make some summaries, and then we'll be done. So for y equals 4 to the x, it says what's the value of b? Well, up here we talked about an exponential function. B was the base, and so b is the thing being taken to the power. And so right here, the value of b for this is 4. This 4 is to the power of x. What is the value of a? Well, there isn't one. It's just 4 to the x, which means my scale factor, it's the same thing as writing 1 times 4 to the x, which means my a is 1. Well, this is 4 to the power of x. We want to know if it's increasing or decreasing, so we'll graph it on our calculator and we will look. So we have 4 to the power of x, then we'll graph it. And it's positive, so it should increase, and so there you go, it is increasing, and so we get to say that it's an increasing function. And when I was looking at that, I happened to notice that the y-intercept was still at 0 and 1, because that's what it crossed the y-axis right there at 1. And so then the domain and the range, well, it goes on forever in both directions because I didn't limit it at all. So my domain is all real numbers and my range is all y values greater than 0. So now let's talk about what happens if I multiply it by 1/2. So I'm going to take 4 to the power of x and I'm going to do it by 1/2. So we're going to go back to our calculator, and this time I'm going to put it in the second one. So I'm going to do 0.5 times 4 to the power of x. And I'm going to graph that one so I can compare it. And so there it is. That one increases at a slower rate. Okay, it's not getting as big as fast. So now we're going to look at it. My y-intercept looks like it's right there between 0 and 1. We're going to call that 1/2. So when we're writing it down, my b is still 4, but now my value of a is 1/2 because my scale factor is now 1/2. I've made it half as big or half as fast, and it is increasing still. This time my y-intercept was at 0 and 1/2. So maybe we can make a correlation between y-intercept and our scale factor. We'll talk about that. Just like the other one, domain's all real numbers, and the range is all y values greater than 0. So how does 1/2 times 4 to the x compare to 4 to the x? And when we looked at that graph, you should see that they're both increasing. This is 4 to the x, the blue one, and then the red one is 1/2 4 to the x. They're both increasing, but the red one is increasing slower. It takes longer for it to get up here to these numbers because it takes longer going on the x value. So if x is time, we're taking more time to get there. So it increases at a slower rate than the original one. So when I multiplied that by a fraction, it increased slower. When I multiply it by a whole number, it increases faster. And then when I put a negative in front of it, it makes it reflect. So I'm going to give you a second. I want you to pause. I want you to see if you can do the table and answer the questions for number 7, and then come back and check your answers, and then we will summarize. So here I have my table filled in. I just used my calculator like before. I typed in 0.5 to the power of x, and then I just filled in my table, and all those fractions were easy to use. And so there it is. I plotted my points, made a graph, and you should see this time the graph is decreasing because from left to right it starts big and then gets smaller. The y-intercept is still 0, 1. That's where it crosses the y-axis. And then the value of x, where f of x equals 0, also does not exist, because just like the graph that was increasing we did before, that's never going to reach 0. It's going to get really, really close, but it's never actually going to be 0. This is the paper folding exercise you did yesterday, because you're cutting it in half, and then you're cutting it in half, and then you're cutting it in half, and then and you can cut it in half all day long, but you can never cut it in half and not have anything, because you started with something. So it doesn't exist. It's a decreasing function, like I said, because it goes down from left to right. The domain is all real numbers, and the range is still y is greater than 0 because that entire graph is above the y-axis. If the graph were below the y-axis, like it was when we did the negative and it reflected, then it would be y is less than 0. But this one is still just y is greater than 0. So let's summarize. So for y equals a times b to the x, b for your base, if b is a number between 0 and 1, which means it's going to be a decimal or a fraction, any number between 0 and 1. It can't be 0, it can't be 1, but if it's a fraction, a decimal, whatever, then you end up with a decreasing function. Just like the one we just did. It was 1/2, and so it was decreasing. If b is a number greater than 1, like we saw just a second ago, then you get an increasing function. Now, if I put an a in front of it, like we did over here at the top of this page, I had 4 to the x, and then I had 1/2 times 4 to the x. And then over here we also did the same thing. We put a number in front of it, and we did 2 times 3 to the x. And so we're going to talk about what happens when we do that. And so if I change the a value, so I change my scale factor and I make it a fraction, then what happens is this has a slower rate. It either increases or decreases, but it does it slower. Just depends on what kind of function you have. And then if a is a number bigger than 1, then it has a faster rate. And if a is a number less than 0, well, a number less than 0 means it's going to be negative. And so when I had it to be a negative, what happened was it reflected. And so then it is below the y-axis. And so now it flips over and it's going the opposite direction. And so that's what happens. This is the summary you need to keep up with. So you need to understand that if you have a fraction to the power of x, it's going to be a decreasing function. If you have a whole number to the power of x, it's going to be an increasing function. If you have an a, so if your scale factor that you're multiplying by is a fraction, then it's going to increase or decrease at a slower rate. If it is a whole number, then it's going to increase or decrease at a faster rate. And if it is a negative, it's going to reflect it. So we'll talk about all of that when y'all come to class tomorrow. I will see you then.